Hi again, welcome to another review session for your final exam in Calculus 3208 from CDLI. Today we're looking at something called sigma notation. Sigma, a Greek letter sigma, this guy. So sigma notation and Riemann sums. So what is this all about? Well, as we're going to see, sigma, this notation that we have, is just a more convenient or concise way to write out a sum. It's just a fancy notation, so we don't have to write out all the terms if we want to imply a sum. And then we're going to learn how to write Riemann sums using sigma notation. All right, let's get started. So this is sigma notation broken down into all of its sort of component parts. So you see for a sigma notation we have stuff on top here and stuff on the bottom and this big thing over here. So basically let's see what sigma does. Okay, we'll start right down here with this guy. This is I. I is called our index variable. So basically a sigma notation allows us to write one notation to represent a whole slew of terms that we're going to add together as a sum. And for each one of those terms, I is kind of like your term number. We can change it a little bit, as you'll see, but if I equals 1, you're talking about your first term. If it equals 2, you're talking about your second term. We can start when I equals 4. We can start with the fourth term instead of the first, or we can start when I equals negative 27 if we like. But the idea is every time I increments or goes up by 1, then what we do is we jump from one term to the next. Then we just have to sort of tell our sigma guy where to start. So this m right here is the first value of I that we use. Typically it's 0 or 1, but we can use anything we want. And that helps us create the first term. And n tells us how many terms we get to, but it's not really like the number of terms. It's the index for the last term in case we don't start at 1. If we do start at 1 and we go up by 1 every time, then n is going to be equal to 10. If we've got 10 terms, it'll be 100 if we've got 100 terms. But sometimes we start in funny places. So it's the last value of I that we use to create the last term of the series. Okay? So what does sigma do? It tells us to write out all the terms and add them together. So it indicates a series. Remember from your study of sequences and series in previous courses that a series is basically a list of numbers or elements that are all added together. So then there's this bit right here, which looks kind of weird, and this is kind of the most important bit. That's the formula that I use to generate the actual term for a given value of I. So that tells us how do I compute each individual term as I increase I from one number to the next to get all of those terms. Okay? So this is a function or a formula that we use to get every different value of those terms. All right, so there's a lot of stuff there, and it always makes a lot more sense when we throw an example at you. So let's do that. Evaluating a sum from sigma notation. So here's the sigma notation that we're going to start with for this one, right here. And this is what you would be given. It says sigma from I from 1 to 4 of 3i minus 2. So basically, it says to create 4 terms using this formula, starting when I equals 1 for your first term, up to I equals 4 for your last term. So the first term will just be 3 times I minus 2, which is 3 times 1 minus 2. Then the second term will be 3 times 2 minus 2, 3 times 3 minus 2, 3 times 4 minus 2, etc. until we get them all figured out what they are. And so all those numbers turn out to be these guys. Add them together, and we've got our sum evaluated. That's basically all there is. That's what sigma means. We can go the other way, though. Sometimes it's convenient to start from quite a convoluted or ugly-looking series and try and sort of break it down so we can rewrite it in sigma notation. So let's take a look here. Let's say we were just given this series. Okay, so before we look at any of the stuff below there, let's just try and diagnose what's happening here. So for that particular series, we've got terms that start with 12, then 8, then 4, then 0, then negative 4, negative 8. So we can see that from one term to the next, we're decreasing by 4 units all the time. So you should know if that's the pattern that you see, that's an arithmetic series, which corresponds to linear functions, but it's discrete instead of continuous, right? So each term we can write as a formula. So the formula for any one of those numbers, depending on which position it's in, would be 16 minus 4 times I, where I is kind of like your position number. Okay? So for instance, your first term, T1, would be 16 minus 4, which gives us 12. Your second term, 16 minus 4 times 2, which is 8, etc., all the way up until the very last one, which will be 16 minus 4 times 6, and that's equal to negative 8. Okay? So if I want to represent this, instead of finding out what it equals, I just want to represent it in sigma notation, I would say I'm going to start when n equals 1, or sorry, I equals 1, and I'm going to go up to n is usually what we call our last number, remember? N equals 6, and I use the formula 16 minus 4i to compute each term. Okay, so that's how sigma notation works. Going one way when we use it to produce the terms, or use the terms to create the sigma notation. Let's look at some examples, shall we? Okay, so it says evaluate each sum. First one doesn't look too hard. It says start with I equals 1, go up to I equals 3. So that's a whopping 3 terms we have to add together. And it says to do that for the formula 5 times I squared. Okay, so 5 times I squared. So the first term is going to be then 5 times, where it says to start, 1 squared. Plus the second term will be 5 times 2 squared. And there's only 3 of them. The last one we have is going to be 5 times 3 squared. So if we have to compute or evaluate the sum, that's 5 plus 5 times 4 is 20, plus 5 nines are 45, and that gives us a total of 70. So that sigma has a value of 70. It's kind of funny when you think about it that this means 70 in some strange convoluted math language. Okay, so now we're going to go from I equals -2 up to +2 using this formula. So like I said, you don't always have to start with I equals 1. You can start with I equals anything, but typically we start with 1, but we don't have to. So this time we're going to actually have 5 terms. For -2, -1, 0, and then 1 and 2. So our first term for this one is going to be 8 subtract -2. Our second term is going to be 8 subtract -1. And our third term will be 8 subtract 0. And 2 more. We're going to have 8 minus 1. Plus the last one will be 8 minus 2. So we put all of our terms together and we've got 10 plus 9 plus 8 plus 7 plus 6. Okay, so let's see what this is going to give us then. 2 times 16 is 32 and 8 is 40. There we go. We got 40. So 19 plus 8 is 27 plus 7 is 34 and 6 is 40. So we've got 40 altogether there. Okay, next example. It says write each sum using sigma notation. All right, so this is a little bit trickier because we have to figure out what the pattern is in the term so we can write the formula. Then after we have the formula, we can write our sigma. So it's usually easiest to do that if you let your values for, oh, I wrote T and I meant to write I. If you let your values for I start at 1. So let's say we got first, second, third, fourth, and fifth terms here. And the next thing you can try to do is look for a type of sequence or series, in this case, that you recognize. So I go from 17 to 21, that's an increase of 4. And then 21 to 25 is another increase of 4. These are increasing by 4 at every single step. So I'm going to say that this is probably going to be an arithmetic sequence. Well, I know it is an arithmetic series. And it's going to have a common difference of 4. So I'm going to say that Ti will be equal to 4 times my index. And then I'm just going to choose a number that I could use to start us off if my first value of I is 1. So if I equals 1, this is 4. And to make 17, I'd need 13 more. So that's not probably the way you were taught in grade 11 to write the formula for an arithmetic sequence, but it's a quick way to get it done. So then what we have to do is we just have to write our sigma notation. So I want to add up stuff that I derive using the formula 4i and 13. Okay. And I'm going to start from I equals 1, we said. And I have 1, 2, 3, 4, 5 terms, so the last one I'm going to need is I equals 5. And so there's that series written in sigma notation. Okay, let's try another one. In this case, what have we got? We got 1, and then 8. We went up by 7. And then to 27, we went up by 19. Definitely not arithmetic. We could look for a quadratic sequence, but it's probably not going to be that either. Let's see, is it a common ratio? Is it 1 times something going to give me 8? So that would be multiplied by 8. And then times 8 again. Nope, that's not going to work either. Whoa, what's going on here? Let's see if we can see another pattern. 1, 8, 27, 64. Do you recognize them? That's 1 cubed, plus 2 cubed, plus 3 cubed, plus 4 cubed. It's just the first 4 perfect cubes. So if we think of our values of I as being 1, 2, 3, and 4, we can go ahead and write our sigma, because our notation here is just going to be I cubed. We want to add up from I equals 1 up to 4, the first 4 perfect cubes. And there's our sigma notation. All right, fun stuff. Next, write the general formulae for the Ln and Rn Riemann sums using sigma notation. So we want to take these Riemann sums that we have formulas for that we kind of derived at the end of our last session, or that you may have done before, and we want to write them using sigma notation. So basically the sum business is this business right here, isn't it? Well, this doesn't really look too bad at all. We're just going to say Ln. I'm going to write this out 2 different ways. Ln. Now, this stuff right here doesn't change. That's the width of the interval, b minus a, divided by the number of rectangles we have, n. So that's the width of each subinterval. So I don't have to change that every time. I'm just going to leave it out for now. And what we can do is we can write the rest of it as just the sum of all of the f of x values when we use xi as our given endpoint. And this is a left sum because we start at 0 and go not to the very last, but the second last, n minus 1. So I'm just going to say I equals 0 up to n minus 1. And then depending on how many subintervals I was using, etc., I could alter that. I'll do something similar over here for Rn. I could say it's b minus a over n. And I'm going to write another sigma to represent that sum. And I'm going to go from I equals 1 all the way up to n this time of f of xi. So really the only difference between these is that instead of starting at 0 and going to n minus 1 like we do for our left-hand sum, our right-hand sum starts at 1 and goes to n. One other little trick though, you don't often see it written this way in the textbooks with this b minus a over n. More commonly what they like to do is they like to call that delta x. And there's good reason for that we'll see in one of our upcoming review sessions. If you haven't seen it already, you probably have. No surprises left. This is review stuff. So if I have I equals 0 up to n minus 1, you can also say instead of just f of xi, remember that this bit right here, that's delta x. So that's the width of each subinterval. So sometimes we call that delta x. And some folks like to leave that inside the sum for good reason. We'll see later on because we're going to do some stuff with limits, and it's more convenient to have it's inside the sum because it's affected by the limits. So we're going to have Rn equals, we're going to have a sum again from I equals 1 up to n. And another way to write that one of f of xi is just going to be the same thing multiplied by delta x instead of just by b minus a over n. Okay, so not a whole lot to that stuff. It's not the most difficult thing that we've done, but certainly it's an important idea. It's just mostly what we want to do is make sure at this stage that you understand what sigma notation is so that when we go to do some limits with it and stuff later, you won't be confused of where this funny Greek letter is coming from. Anyway, did anybody notice that the Greek letter sigma is roughly equivalent to the Greek letter s, right? That's why we use it for sum. Neat. We use the letter pi for multiplying though. I haven't figured that one out yet. Okay, product maybe? Pi, p, okay. Evaluate each sum. So this is the your turn question. So same kind of thing that we did. You just got to take those and write out what the terms are and add them up using sigma notation to evaluate sums. Go for it. All right, so that's good stuff. And then there's a solution for that. So we worked it out and got a sum of 20 for the first one, 105 for the second one. Nothing terribly complicated, but lots of fun anyway. And let's summarize some of our key ideas that we've talked about here. So some of our key ideas, we started with sigma notation is a shorthand notation to write out a sum. So it saves us writing out, especially if we have a big sum with lots and lots of terms, saves us writing them all out. We can just write it really concisely in this form. So sigma notation is particularly convenient for long series with many terms, of course. And sigma notation can be summarized, get it, a little humor, summarized as follows. I is the index variable. M is the value of I used to compute the first term. Okay, so the first term we get by using M, and n is the value of I we use to get the last term. That seemed a little bit weird at first, didn't it? But now it's okay. So f of I is the formula we use to compute each term for the current value of I, or whatever value of I we're using for that particular term, of course. I really hope that that stuff is helpful, and I hope that you're learning lots and that your review for your final exams is going well. Do not hesitate to post questions up on D2L. Please do so. Love to try and help you out if I can. So good luck studying.